computer. Excellent. So now we are recording. So, okay.
Yes.
It's a convener.
Thank you, Pavla. Okay, so let's start the session 2. Welcome on site and online, everybody. And our first speaker will be Susan Kaspari from the Central Washington University, USA. And her topic will be the role of light-absorbing particles in snow and ice on Svalbard, on focus on dust.
So let's take the presentation. And then share. Is it doubled now? Yeah.
Yes.
Okay. So please go ahead.
Thank you, Ati. Okay, good afternoon. This is early work that I did last year. I was on sabbatical in Norway and was working at the Norwegian Polar Institute. And so this is the results of the work that we were able to get done so far. And then we have plans to continue this work. So this is probably familiar to many of you. You all know that the Arctic is, of course, warming, but the warming is really pronounced in the region around Svalbard. And so it's an area of lower elevation glaciers that are particularly sensitive to climate change. And one of the impacts of that is that we're seeing widespread glacier retreat. And so this map over here, the areas in red are showing more so loss in the height of glaciers, but a lot of loss. And so that's largely attributed to, shows a strong sensitivity to temperature increases. But another factor that is at play there,
I just removed the participant. Please.
okay, yeah, another factor that is at play there is also the deposition. Maybe if we shrink it, there we go. Okay, perfect. So temperature, of course, is a major driving factor of the glacier loss, but another factor at play is the deposition of light absorbing particles. So this is probably review for many of you, but black carbon is really widely studied. Dust from various sources, including rocky outcrops, arid regions, land use change. You all know this very well. We also get colored organics and then volcanic ash, like you have here in Iceland. And so from a snow perspective, we're interested in this because it lowers the albedo. So if we have a really nice clean snow, most of that energy gets reflected back out to space. But when we contaminate it with these particles, then that darkens the surface and causes more energy absorption and faster melt. And so in Svalbard, there's been quite a bit of work done with this, looking at black carbon. And so there's lots of studies that have investigated this. And my background is looking at light absorbing particles in other regions around the world. But when I started to do my literature search in preparation for spending time in Norway and for doing work on Svalbard, I was really surprised to just find no measurements of the dust concentrations in snow. And so there were some really good measurements available of how much dust was in the atmosphere, but very little to help constrain dust deposition on Svalbard, either seasonal snow or on the glaciers. And so the few measurements that were available were definitely not ones that were representative for really seeing what's happening over the archipelago as a whole. And then there's been a little bit of work that's been done on organics, but I won't talk about that today. So there's a number of recent studies that are highlighting the need to investigate dust deposition in snow and glaciers. So a few of those are coming from 2023 and another one from 2019. But there's definitely an increasing acknowledgement that we have this big knowledge gap in dust deposition on the snow and glaciers in Svalbard, and that there's a need to be able to see how important the dust versus the black carbon is. So the research that I was looking at was trying to answer some of these questions, which is, what is the relative contribution of black carbon, dust, and organics to snow albedo reductions on Svalbard? What are dust concentrations in the Svalbard snowpack? Because there's just hardly any reported measurements of that. What are the actual dust deposition rates? And then how variable are Svalbard dust sources optically? And how is dust deposition changing? So I was working on a few different sites So I was based out of Ny-Ålesund for most of this work, so working on the typical suite of glaciers that are monitored by the Norwegian Polar Institute. And then I also did some work on Drømbrain down here further in the south that is accessed out of Longyearbyen. And so in the field, we would first measure snow reflectance, and then we would collect big bulk samples of snow, snow pits, and then we were doing shallow snow coring, usually going no more than about 5 meters depth to be able to sample the seasonal snow. So there's a wide range of techniques that we normally are using to be able to characterize the light absorbing particles, but the Norwegian Polar Institute is much more kind of a logistical based institute. We didn't have analytical facilities there. So I was pretty limited in what I was able to do with the samples last year. And so mostly what the results that I'll show you today are based on total particle concentration. So just doing simple gravimetric filtration to get an idea of the total particle mass. But normally, back in my lab, we're doing using an SP2 to measure black carbon, a thermal OCEC analyzer to get at organic and elemental carbon, and a thermal analyzer to partition out the dust versus the organics. And then we have plans to do more. Oscar will be talking later on about plans for his master's thesis, where we'll be doing more work in terms of characterizing the dust using scanning electron microscopy and also ICP-MS. And then we use different methods to look at the dust optically. So to start with, another simple method I was able to employ while in Norway last year was measuring filter reflectance. I want to be able to do more work. This is a method that's being used in Denmark to be able to separate out the organics from the dust and then be able to measure the mass absorption coefficient. And then I have a hyperspectral microscope where we can measure the spectral reflectance of individual particles. So that's some of this is more what we would like to do in the future. But the results I'll share with you today are just filling in that knowledge gap of what is the deposition. And so here we're assuming that the mass is being, the particle deposition is being dominated by dust. So we collected snow from, got the full winter snowpack column from various sites around, mostly around the Ny-Ålesund region. And so this is showing the results from that. So dust particle concentrations in the snow during the wintertime are quite low as expected. There were some things that were interesting. If you look at the sites that have higher concentrations, like at Kongsveien and Holtedelfana, some of that I think is a relationship to both differences in the bedrock geology and the material that's there. And then at lunch today, we were just talking about some of the things in terms of the importance of wind. And there are a lot of winds that are coming down glaciers, such as Kongsveien, that are causing some additional weathering of some of the dust sources there, and I think make that a little bit more active for local dust sources. So this was just really useful for us to actually have some measurements of what dust concentrations in the snow are. So that's from the winter. These are measurements of different studies that are looking at the accumulation rate of dust in different settings in Svalbard, and so highly variable. You know, in some places, very, very high accumulation. And then here, Kavan was sampling in some snow gullies later in the summertime. So not representative of what was happening around Svalbard, but gives some constraints in terms of the actual deposition rate. So these are the results then that we had, and these are just winter particle deposition rates, showing the variability that we were seeing, and so quite low with median values at about 0.4 grams per meter squared. We also did use this simple technique also to be able to just look at dust deposition with depth. So here's a couple shallow cores from Kongsveien and Holtedelfana, and it's 2 cores to get at some of the full variability in terms of seasonality. But it shows some of the variability that we observe with depth. So I also went up and had taught up at UNIS, the University Center in Svalbard, on a course, and that was fun. We were able to work with the students and drill some 10-meter cores, and we were able to get some really nice dust records out of that. and I'll be going back up there. I leave tomorrow afternoon, and we'll be back up in the field this weekend collecting more of these cores. So this is visually what those look like. So this was the prior year's summer layer, so you can visually see high dust concentrations there. And from the satellite imagery, you can also see the presence of dust. So here we have that, and then over here as well. But we have, in this region here, we have very little snow that's remaining through the summer months. And so in terms of places on Svalbard that are closer to these bigger dust sources, we're limited in how many sites are actually preserving this record. And I'll talk about that briefly at the very end. So I was pleased, just not knowing what we were going to get when we actually started to do the filtration of these cores. And so the way to read this is starting at the top of the core and going down with depth. And so because we were only visually able to see that one dust layer that I showed you in that picture. But when we actually went through and did the filtering, you can see that we actually were capturing some nice seasonality, and that there was quite a bit of dust actually getting deposited on that glacier. And so this is the resulting records that came from that work. So we had one core that was 5 meters and another core that was 10 meters. And those filters are just showing from the higher dust events, and that's happening. The higher dust concentrations are happening during the summer and into the early fall. And so we're capturing seasonality and interannual variability and how much dust is being deposited there. So we have more work to do with that. And then this weekend, we'll be capturing an additional core to match this record and be able to extend that up to present. So another thing about working there is that just traveling around Svalbard, you can just very visually see very different sources of the dust. So over on the right there are different places where we were working, where you can just see that the bedrock geology is really different. And this is just showing the bedrock geology map over here on the left. And there's some places that are much more likely to be active dust sources, like up in here, that are much more sedimentary in nature, whereas there's other places that are not weathering as well. And so definitely in terms of starting to investigate what the local dust sources are, it's highly variable depending upon where you are in the archipelago.
1 minute.
Oh boy, okay. Okay, so this is just to say that, so we were measuring filter spectral reflectance, and this is just to show some of the pictures of what those filters look like, and that we can really see that that there's differences in the filters. We can also pick up the organic signal here that's associated with the presence of snow algae. One of our major things that we were interested in was all of the emphasis has been studying black carbon, and we're interested in what the snow albedo lowering effect is. And so we did modeling based on the prior reported measurements of black carbon and what we observed with dust. And what we found here is that if you look at the signal from dust versus dust plus black carbon, it's really the dust that is the major factor that is driving the black carbon lowering. And then I know I'm just about out of time here, but what I'll end with is just touching on the same thing that many of you have talked about, that we've got this glacier retreat that is now exposing these additional areas. And so we're getting more active dust storms. And so one of the things that I want to be doing in the future is getting out to some of these valleys that are much dustier and trying to sample places where we still have glacier fern that is remaining, so that we can start to look at how consistent is this signal across the region, or is it really spatially heterogeneous? So I think I'm out of time here. So I'll just leave this up in terms of what our preliminary results are and what our goals are for our future work. And do we have any time for questions?
Yes, we will have 1 or 2 questions.
Okay, are there any questions?
Question there, please.
Can you always please walk to the microphone, because I was informed it's not very well heard from.
Okay, first, great talks. how much do you think, what's your opinion regarding the albedo? It is about the color of these dust particles or actual mass of the deposited materials on the snow? What is the dominant process?
My assumption right now would be the total mass, but we can see that we have a difference as some of that dust material is more absorptive than others. So yeah, so I think both matter, but I think the total amount of dust is what's most important. A lot of the places like up in Holtadalfana, the dust concentrations are quite low. Yeah.
Thanks.
I would have one quick question.
Yeah.
You mentioned also ash, didn't you?
Yes.
So what is the contribution from ash and how do you analyze it, separate it?
Yeah, we haven't, I mean, because I was only doing that filtration, we haven't been able to look for any signal of that before. I know that there's other studies that have shown that ash is getting over there, but just visually looking at it and, looking at what this landscape looks like, I guess for me, I have a hard time believing that the ash from Iceland, unless you had some really active eruption, is actually playing that huge of a role. Like when you have this right there next door, this is going to be a bigger source.
Yeah.
Yeah.
Thank you.
One more question.
Okay,
So,
one.
Claudia Di Biagio on the
Oh, I just
screen.
checked the chat and I didn't realize.
Yes, I have one question. I cannot see the chat for writing, so I would do. She has showed that as a function of the depth along the core, the highest concentration were found in summer. So this is an indication that the local sources are dominating the deposition to you, or do you have any other indication or any kind of analysis that can
We haven't. So like I said, we've only done these really simple filtering. So in terms of actually having measurements that would help us to pinpoint provenance, I don't have that yet. But I do think that the local sources are what's dominating. And based on what we see in the seasonality and what's known of when long range versus local sources are coming in, I think it's definitely local that's dominating the signal.
Okay, thank you again, Susan, for the most interesting talk. Okay, and next speaker will then be check Arnold Downey from Canada, from Université de Montréal. So welcome. Have your talk. So it's this one, right?
Mm-hmm.
And then okay. Okay, good.
Well, yeah, how do I make it just so I guess it's okay. That's fine. Okay. Hi everyone, thanks for coming. My name is Arnold. I'm with the Hayes Group at the University of Montreal. My study has more to do with the health impact of high latitude dust and of particulate matter in general, but specifically for high latitude dust because it doesn't receive much attention, as we all know, so it's gaining more. And in particular, the central question of my research is what influence could glacial sedimentation processes have on the health implications of high latitude dust? It's sort of a very unique interface, but I think there is some implications there in understanding what kind of impact dust has on health outcomes. As we know, mineral dust can play a large role in certain health outcomes. For example, silicosis is a endemic known that's related to dust of all latitudes. Also, lung inflammation can result from exposure to dust, as well as certain cancers. And the extent of the human health outcome related to exposure to particulate matter is related to the size distribution of the particles inhaled. For example, PM 2.5 is known to pose a greater health risk than PM 10 on a per mass basis. And some metals in particulate matter have known associations with carcinogenic and non-carcinogenic health outcomes. For example, arsenic or manganese has a minor one as well, and chromium. So taking the composition and size of particles into consideration is important for determining health outcomes. But then how does this relate to glacial sedimentation processes? So glacial sediment is produced by the movement of glaciers that results in class-on-class abrasion, creating very fine particles out of large rocks that originate in the glaciers. And usually this grinding process brings particles down to an ideal terminal size. And this has shown to actually relate to the metal concentration in the till or the glacial sediment. This was given a fair bit of detail, or this was given some attention in the 80s in Canada, mostly for the purposes of till prospecting, which is used for mining purposes, for example, tracing a metal concentration to an ore source that is used to determine where mining might want to be done. But in studying this, it seems to explain something I've noted in my dust research that I'll go into in the next slide. And that is that the metal concentration tends to vary with grain size quite drastically. For example, large grain sizes, as we look at figure 3, don't tend to have as great of a metal concentration or metalloid compared to finer grain sizes in the 1 to 4 micrometer size range. And this is true for a whole suite of metal. It's not just for the 3 elements shown in figure 3. This was shown for dozens of elements. So there's something related to basically the hardness of these minerals and where they end up in their terminal sizes once they are ground in the glacial processes. And then the second process that's at work is related to the weathering of metals in the upper till or in the upper sediment. Basically, this is fluvial processes such as water flow, redistributing metals that are contained in upper levels of sediment to lower levels. And it's likely that small particles with a high surface area to mass ratio would be sequestering metals as they're released in these weathering processes. So these combine to have a greater metal concentration in fine particles. So not only do fine particles have a greater influence on health outcomes to begin with, then also they have higher metal concentrations in the case of mineral dust. So to study this in practice, we have our study site in Iceland Valley in Killarney National Park, Yukon, Canada. That is the same location Daniel pointed out earlier. Southwest Yukon. Basically, we have this sampling setup in the valley where we were able to have a cascade of particulate matter samplers, both at 3 meters and 6 meters above the ground. But for the purposes of this study, the important thing is that I ended up with a collection of TSP, which is total suspended particles with no size discrimination, PM10 and PM2.5 samples. And in analyzing these for total metal concentration using ICP-MS, a pattern arose where the finer size fractions tended to have significantly greater metal and metalloid concentration than the total size range. As we see with arsenic, it jumps from around 10 micrograms per gram in the total suspended particle size range up to around 20 in the PM10 size range. And then a bit of a jump as well, going from PM10 to PM2.5, although it wasn't not as significant as a difference. But this reflects what was found in the Schultz research in the 80s, showing the increasing metal concentration with finer sizes. And this was consistent with most elements that were analyzed in this fashion, which is consistent with the till research as well. Then the next question is, these sediments and these dusts have high metal concentrations, but then how much of it is actually implicated in health outcomes? To look at that, we consider the bioaccessibility of the metals in the dust, and that's it's important for calculating the daily exposure to metals or to any pollutant in general, which is usually done with equation 1, which includes the concentration of the dust as well as concentration of metals total and the concentration of the dust. But then the bioaccessibility is also a proportionating factor in this equation. However, it's not very well studied, I mean, for particulate matter in general, but especially not for dust. And most methods for determining the bioaccessibility of metals in particulate matter, well, they aren't very well established. Contrast to gastric bioaccessibility of metals, which has, you know, very well established methods with EPA and things like that. So I had to basically go into the literature to find what method I was going to use for this. And Dr. Forenza Kasturi did a fair bit of work on finding the optimal method for determining this. And the method she landed on has an optimized, you know, she determined which lung fluid, simulated lung fluid is good for this, and which, you know, agitation method is used, and what agitation time period is used, because all these things were not standardized before. And I took this method and took it a step further with being able to apply it to filter samples. Most of the time it was applied to bulk particle samples, which isn't, but applying it to filters has its own advantages as well. So basically I take half the filter, I determine the total metal concentration, and then the other half of the filter goes through the same kind of processes that the particles would go through in the human body. That is, it spends about 24 hours in the lung at body temperature at, you know, the appropriate pH, and then it spends time in the gastric phase and then time in the intestinal phase at the appropriate time periods. And in doing this, I have some, oh yeah, this is what it looks like when the particles are being, you know, they get to dance for an entire 24 hours. So kind of a fun little process. This is just for the lung phase. And then I have some preliminary results from doing this, both for high latitude dust as well as for urban particulate matter that we sampled last summer in Montreal. So looking at the urban particulate matter, we got some similar results comparing to another researcher that did the similar, you know, a similar method like this, which is Liu 2023. For his samples, they were taken in Hotan City, China. But we see, even though they're, you know, different source areas, the bioaccessibility results are quite similar, except for arsenic. I obtained a higher bioaccessibility for arsenic in my samples than compared to him, but for cadmium, lead, manganese, they're very similar. And then for my mineral dust samples, it was kind of in the infancy of my method development, so the detection limit was still kind of high, but I was still able to quantify for arsenic and manganese. But these showed to be quite similar to the method that Kasturi originally developed for her measurements on a Montana soil CRN. And I thought this would be the most appropriate matrix to compare with, since they're both kind of soil or sediment-based materials. But then the values I determined for arsenic and manganese lined up with those that Dr. Kasturi determined as well. So where do I go from here? Is that I want to further expand my inventory of samples and determining different source regions for the bioaccessibility of metals in the dust. So this is kind of, you know, if anyone's interested in or has samples of dust available, that particularly if they're relatively high in mass, and if they're on quartz fiber, that's kind of ideal. But I'm open to all sorts of sampling materials, like if it's on polycarbonate or if it's on Teflon, those are open as well. And then what's in it for you is that I determine the total metal concentration as well, which is a sought after parameter, and I'm not too bad at doing that either. I have a fair bit of experience. So if you want the total metal concentrations in your samples, send them my way. I would be very happy to collaborate. And I think this would be a really great, really great database to start building. So, and these could be your samples. Your samples could dance just like them. So here's my email, or that goes to my LinkedIn profile as well. You can contact me in that way, and I welcome any questions.
Thank you for keeping time, and thank you for the most interesting talk. So are there any questions in the audience?
Yeah.
Are you able to do it with cellulose filters? And then what do you do in terms of acidification?
In terms of acidification? Yeah. So yeah, I would be able to do it with cellulose filters. The only, like, I'm very welcome to any kind of, I can't be picky with the filter too much. I would just have to validate the method with that filter because I don't know what kind of elements might leach from the filter material itself. But that's an easy step. I mean, well, anyways, it's fine. And then in terms of acidification of the samples going through the bioaccessibility path,
You're just
you
prepping
mean?
them for ICP-MS. I'm just wondering what you like in terms of what your acid treatment is.
So for the total metal concentration, it's I do an aqua reagea mixture, which is 4 mils of HNO3 and 1 mil of HCl. Then it goes through an acid through a microwave digester. And I obtained good recoveries greater than 80%, at least for most elements. But these have been determined for a suite of elements, and it's relatively effective. And then on the for the bioaccessibility section, it's like basically neutral pH for the lung fraction. It's very low pH for the gastric fraction, which is 1.5 to 2 for pH, and then the intestinal phase is neutral again. It's around 7 pH. But I'm welcome to cellulose filter samples as well. So
Okay. Any more questions? Yeah, I think this is an excellent thing to come here and present interesting results, interesting topic, and not only sharing that we would share like the dust samples, but also the filter samples as well. So many people, for example, at FMI, we have a lot of quartz filters, but we don't actually determine dust on those.
Yeah, that's the perfect thing I'm looking for, because if people do gravimetric measurements of dust and they've just been used for like the filters for gravimetric measurements that were used in the past, and then they're just sitting around, then it's perfect for this because I can just take them and do them, and then you get metal concentration along with the bioaccessibility as well. So that's kind of what I'm going for.
Perfect. Thank you so much.
Thanks so much.
Okay, and our next speaker will be online. I can see very nice Teenu Hevgadottir from Agricultural University of Iceland. So welcome, and the floor is yours. You are welcome to share your screen.
All right, so I hope everybody can hear me nice and clearly. Yeah, so my name is Teenu Hevgadottir. I'm here to present my results from my thesis, my master thesis, and just a quick overview of my presentation, starting with just a short introduction on the topic and the study area, and then I will follow by a simple description of my methods, and then moving on to the main part, which would be the results and discussion. And then I will briefly mention some of the main conclusions. But this was the title of my thesis, which I did as a part of my double Nordic master's degree in environmental changes at higher latitudes, which I did through the University of Helsinki as well as the Agricultural University of Iceland. And my supervisors were Andrei Gunnarsson from Landsvirkjun and then Ekaterina Pesova from the University of Helsinki. But just kind of to clarify the main objective of the study, it was essentially to analyze and quantify the melt enhancement initiated by deposition of mineral dust from a single dust event over the melt season of 2022 on Tungnaárjökull Glacier, which is the southwest outlet of Vatnajökull Glacier. But as we all know, of course, ice caps and glaciers worldwide are experiencing mass loss as well as shrinkage. And now one of the major contributors in the response of glaciers to climate is albedo, as it of course governs the quantity of absorbed solar radiation, further making it a very important driver of changes in both energy balance and surface mass balance. But then moreover, absorbed solar radiation is also considered the main energy source for melting glaciers in Iceland. But the albedo can of course be strongly affected by light absorbing impurities such as mineral dust, which is of course the focus of this particular study. But the mineral dust can be deposited on the glacier surface, causing of course albedo reduction. And additionally, the albedo reduction due to the deposition of dust can be compounded by the grain size effect, of course, which essentially just describes how dust-related heating can then accelerate the growth of snow grains, which then further decreases their reflectivity. But here in Iceland, glaciers portray very high annual variability in surface mass balance, and a lot has to do with the deposition of mineral dust, which originates from glaciofluvial dust hotspots. And we have identified 8 main hotspots here in Iceland. but then the frequency of so-called dust events is kind of controlled by high velocity winds, which of course are very representative of Iceland and other high latitude regions. But then finally, Icelandic mineral dust, as many of you already know, uniquely mainly consists of poorly crystallized basalt, which contains high amount of iron, of course, and this makes it very light absorbing and kind of distinguishes it from the mineral dust produced at lower latitudes. But yeah, as I mentioned, the study area covers Tunarjökull glacier, a southwest outlet of Vatnajökull. You can see the location here of the smaller. But the focus was set on 3 automatic weather stations. Those are located on the glacier, 2 of which are in the ablation areas, TO1 and TO3, and then 1 in the accumulation area, TO6. And their elevations can be seen, or average elevations can be seen here on the slide. But the glacier covers an area of about 327 square kilometers, and it has a negative net annual mass balance of 0.25 cubic kilometers water equivalent. And here, the net balance basically describes the sum of the winter balance and summer balance, and the water equivalent represents the volume of water that would be obtained from melting snow and ice, of course. But the equilibrium line altitude of Tunarjökull is on average at 1,225 meters above sea level. But all right, so a bit about the method. So for the study, I mostly just used data collected from these 3 area sites, but also stake measurements from same sites. But together, stake measurements as well as ADS measurements from Vatnajökull have demonstrated mass loss over the whole glacier every year since the glaciological year of 1994 to 95, with one exception, and that was the glaciological year 2014-15, where we had high winter precipitation in addition to very cold summer, which reduced the melt significantly, and that to a single anomalous year with a positive net surface mass balance. And due to this kind of exceptionally high albedo and cold weather, the data from 2015 was kind of further analyzed in the study, and the albedo was used kind of as a reference for a dust-free surface condition. I will get into that a bit later, but we also get years where we have average negative surface mass balance, especially in relation to very volcanically active years, but also years where we have high suspension of mineral dust, such as the glaciological year of 2021 to 2022. But the measurements from that year at Tunarjökull kind of confirmed a more negative surface mass balance, despite quite a cold winter as well as a relatively cold summer. And this can only be kind of connected with radiative forcing from an extensive dust event, which occurred over the southwest outlets. And that's kind of the reason why I focused on 2022 for the glaciological year of 2021 to 2022, as well as 2014 to 15. But the main part of the method was to use this simple snow and ice melt model, which is basically a model for a daily snow melt using the hybrid approach based on the combination of energy balance and temperature index approaches. And the equation can be seen here, like the upper one. That's the original equation, where K, of course, represents the shortwave radiation. The M is representing the long-wave radiation. And then we have density of water, the latent heat of fusion, and then, of course, the daily average temperature in degrees Celsius. And then this MR, which is basically the restricted mass factor. It has a units of millimeters per degree Celsius a day. And yeah, I will also talk about that a bit more later. But the equation can essentially be put into 2 components. So we have the radiation component and then the heat component. But then, of course, for balancing some units, few adjustment had to be made to the original one. And you can see that down here. Basically, I wanted the units to be in millimeters per day. So this was the end equation. And then, of course, all the data analysis was performed, as well as the statistical methods in Python. But let's move on to the results. So as mentioned, there was a dust event, an extensive one that occurred over the southwest outlets of Vatnajökull from the 7th to about the 14th of July of 2022. And this event caused significant amount of dust to be deposited over these outlets, which consequently, of course, darkened the surface. And here you can see some Sentinel-2 satellite images from before, again on May 28th, and then during the event on July 12th. And you can clearly see how we go from this clean surface, very bright surface, towards a very dirty surface. So what happened? I started by analyzing the albedo data from 2022, as well as the 2015, over a period from 16th of May to 16th of October, as I call here the melt season, essentially. And here we can clearly see the difference both between the years as well as between the two ABS sites, which kind of represent 3 different elevations, of course. But during the dust event, the albedo was estimated to drop by almost 60% here at TO6, which is the uppermost ABS site, so in the accumulation area. So we went from quite very high albedo numbers, so 0.9, and all the way down to around 0.3, only over the course of 6 days. And then in the upper ablation area at TO3, we had a drop of about 35%. So both quite drastic drops, but then only a minor decrease was observed here at site TO1, so in the lower ablation area. But these drops could not be explained by temperature or precipitation, and that's why we can kind of conclude that these were probably due to these dust events. But if we just move on, so essentially my study was kind of based on different sensitivity analysis on melt season surface mass balance to kind of different factors, and the factors that I'm going to discuss here are timing of dust events, and then also dust concentration, while we're simultaneously, of course, analyzing the sensitivity towards elevation by using the 3 ABS sites. But this figure here kind of shows how different timing of the 2022 dust event influences the melt at each of the ABS sites. So as I already mentioned, the true dust event occurred in early July. So I kind of prolonged the melt period by moving the event to June. And by doing that, as probably expected, it caused an increase in melt compared to the true 2022 melt of around 290, only 290 millimeters water equivalent here at the lowermost site, and then much higher, like 720 millimeters and 704 millimeters water equivalent for TO3 and TO6. But then the August event, so by moving the event a month later, it also, as expected, caused a decrease in the melt of around 120 or 126 approximately millimeters water equivalent to up to 610 here at TO3, and then again a small one here, 254 millimeters water equivalent. But according to the largest proportional increase and decrease can be kind of detected at ABS site TO3, and then followed by TO6 and TO1. And maybe the reason for this could most likely be related to the location and kind of the behaviors of the location. So here in TO3, we are located in the upper ablation area, where the surface can change from both snow-covered area to a bare ice area over the melt season, which means that if the winter snow layer is melted early, we have bare ice being exposed earlier and over a longer period. But if the snow layer is not influenced by dust and sustained with relatively cold temperature and occasional snowfall even, the albedo will stay relatively high. But then at ABS site TO6, we can experience frequent snowfall during the melt season, and the snow layer with the snow layer never really melts completely. But then for site TO1, the winter snow layer is usually melted quite early, so the dust events do not maybe affect the albedo drastically. But then on to more of the related to dust concentration. So here the figure kind of shows us the influence of dust deposition and how it gradually is increasing with elevation. But then the table here down below, I hope you can see it, reveals the increase in melt in 2022 compared to, for example, average surface mass balance calculations, as well as the hypothetical dust-free conditions. So here at TO1, the 3 different surface mass balance values give very similar results, indicating that the dust event did not really affect the melting process, as mentioned before. But however, at TO3, so in the upper ablation area, and then at TO6 in the accumulation area, we are seeing an increase. And here in TO3, it increased by 16%. So from an average towards the real 2022 melt, and then it actually increased by 37% from like the dust-free conditions. And remember again, the dust-free conditions were calculated by using the 2015 albedo, but the other data came from 2022. But then on the TO6, the influence gets even higher. So then we're seeing 48% up to 75% increase. I mean, between the real 2022 and then the average and the dust-free conditions. And then of course the amount of snow available for melt over the melt season increases with elevation. Consequently, the influence of the dust event on melting grows with elevation, which can kind of be seen clearly here. But some additional discussions, maybe some of you already noticed, but this NOMAD model, excuse me, that I used has a high level of uncertainty, does not incorporate, for example, subsurface heat fluxes or any heat fluxes from precipitation. So basically the fluxes are assumed to be 0. This has been used before, but still can cause some problems. As of course, like the heat flux from precipitations are very small. But additionally, the turbulent heat exchange fluxes are not explicitly calculated, but are more parameterized here by the temperature term, which is then multiplied by the MR parameter that I mentioned before. And this simplicity can also cause margin of error when comparing, for example, the calculated snow melt with the measured surface mass balance, which we have numbers for from each year. But still, turbulent exchange actually becomes less significant at higher elevations. So that's something also to consider. But also apart from maybe the model's simplicity and uncertainties, the difference between the measured and calculated surface mass balance can be assigned to summer snowfall that may be a further melt and is then not kind of like captured in the mass balance state measurements. But yeah, I think I can draw maybe 3 main conclusions here. So daily melt over the melt season was very sensitive to timing of dust events, as may be expected, and especially at site TO3. So a similar hypothetical dust event occurring in June essentially caused an increase in the melt potential by prolonging the period, and then a similar dust event occurring in August, on the other hand, had the opposite effect. But then the dust event in July 2022, we can say that it essentially caused the melt season surface mass balance to be enhanced by almost 1.5 meters above approximately 1,000 meters. So at areas at TO3 and TO6, compared to the hypothetical dust-free conditions. So that, of course, highly alters the net annual mass balance of lunar glaciers for that glaciological year. But then the influence of dust event was highly dependent on elevation, as can be concluded from the different results from the 3 area sites. And the least overall influence was detected at the lowermost site, and then the highest influence kind of varied between the TO3 and TO6 sites. So those are kind of the main, here are some references. But yeah, that's all for me. So thank you for listening, and are there any questions?
Great, thank you, Steinun. This was a great presentation. Do we have questions on site or online? I want to add that your second affiliation is the National Power Company of Iceland.
Yes.
So how do you then deal with this kind of results in practice in the power company? Do you have a comment on that? So
yeah, it's a good
impact on yeah, please go
Yeah.
ahead.
Yeah, so I did my thesis in collaboration with the Latitude, the Icelandic power company, and of course that's why the affiliation, I'm not working for them anymore. But yeah, basically, of course, it is very well known that hydropower is very essential when it comes to electricity here in Iceland, and everything affecting the melt of the Icelandic glaciers, of course, would also kind of affect the hydropower production. So that's kind of the reason for these types of research within that company.
Yeah, thank you for your comment on this. Yeah, so this is a very significant topic. Yeah, also for worldwide, how do we end up with melting glaciers and these power issues? Also fresh water, of course, in places where we have glacier melt as source of drinking water or agricultural watering water. Oh, do we have online any questions? Please write in the chat, and we can also email your questions later to the speakers if you have. Okay, I see no questions here.
Awesome.
Susan, yes, sorry, one question will come from Susan Kaspari. Yes, please.
I thank you for the nice talk. I just had one question, which is that you were talking about the dust being more effective at melting at higher elevations because there was more snow. And I was just curious if that snow is diluted over the snowpack, if the actual concentrations would be lower enough that that effect could be lessened.
Yeah, good question. I think in terms of like Icelandic glaciers are temperate, so the melting of the top snow layer never really is completed. So, and of course, then we can have different types of deposition of the dust. It can either be mixed with snow. Sorry?
I think somebody had them.
Yeah.
Sorry.
But yeah, it can either be mixed internally or so the deposition I also like in my thesis I went further into how can a different deposition either wet or dry deposition affects this. So of course when we have wet deposition there's also like more absorption than with dry. I don't know if I'm answering your questions at all, but but yeah.
Yeah, okay, yes. So maybe if there is more to ask about this topic, you can then email. Yeah, okay. Great, thank you again for your great presentation. Okay, and then it's time to show some brief introductory presentations on posters. So we welcome two posters, and the first one is Oscar Orm, USA, who is here on site, and it's about investigating dust deposition and composition on Svalbard using 2021 Holtedalon Salo ice core or someplace similar. Yes. Okay. Do you have? I guess.
Yeah.
Yeah, it's there. Yeah. Okay. And then we need to share. It was. Can you recognize
Right there,
this
yeah.
one? Yes. Not yet security allowed. Okay, but it came. Okay.
Okay, hello, thank you everyone. I just have a very brief presentation on some preliminary and forthcoming research that I'll be doing with Susan. Yeah, so I will be looking at dust deposition and composition trends in Svalbard by analyzing a 2021 shallow ice core collected from the Holtedalfana Glacier. It's in northwestern Svalbard. So kind of what prompted this? Why is this important? As Susan touched on, the Arctic is warming at twice the global rate, and we're seeing 5 to 7 times greater warming in Svalbard in particular. This kind of amplified warming we're seeing in Svalbard makes it a valuable indicator for how future warming will occur throughout the Arctic. And as you all know, dust functions as a light absorbing particle. So when we're seeing it deposited on these glaciers, it's accelerating that glacier ablation. So kind of how we're hoping to tackle this is just real quickly on the methods. The poster is about, the ice core is about 8 meters long, 8.15. It was collected, like I said, in Holtedalfana by the Norwegian Polar Institute in the accumulation zone of the glacier. We will be cutting it into 3 different sections lengthwise. The largest is coarse resolution measurements, which we will be doing gravimetric filtration, SEM and EDS to glean particle mass concentrations. At a higher resolution, using a separate quarter of the core, we'll be doing ICP-MS for major element concentrations, as well as SP2 for black carbon. And finally, we'll be doing a SNCR modeling analysis for relative albedo contributions between dust and black carbon. And so ultimately what we're hoping to see here is how dust has varied over the past 10 to 15 years on Holtedalfana. And we're anticipating seeing dust being a greater contributor to albedo reductions in Svalbard compared to other light absorbing particles. That was very quick crash course. Hopefully if you have any questions, I would love to elaborate on anything. Yes, so thank you.
Excellent. Excellent. Thank you so much. And we will have the posters right after we have the other poster presented here. So we will go, there is the poster page there.
After the session after, because we will have just 10 minutes.
Yes, okay. Okay, and then, yes, so then we have a second poster by Sara Herrero from Spain, and she is also here on site, and she's from Atmospheric Optics Group of Valladolid, Spain. So, so let's have your poster.
That's one. Yeah, it's a big
Yes, yeah. Let's see this. Nothing's happening.
Oh, okay.
But we have to share it still. Is it this?
Well,
Do you want to
adjust the page?
adjust the page?
Yes.
Is it like from here or
Minus?
minus? Okay.
Yeah, I guess so.
Ah, now I see. Yeah, it's like vertical.
Yeah, sorry.
Yes.
I didn't know I
Okay,
had to
but
present it.
yes, okay, but this is fine.
Okay.
Yes, okay.
Okay, so this is just a continuation of the work I presented before, but for fine particles. So here we identify several fine turbidity episodes that are mainly usually from biomass burning events in the north of Canada and Eurasia. So it's just an analysis. Now we have identified them with the methodology I presented before. Also using the all sky camera to verify it was clear sky. It's what we can do now. We have the episodes. There are other measures I mentioned before. Using sky radiances and using inversion algorithms, we can retrieve a more complex aerosol properties that later my workmate Celia will go deeper into that. Yes, we can have some parameters like single scattering albedo or refractive index from these remote sensing measurements. And analyzing these 5 events, we characterize each event with these aerosol properties, and using radiative transfer models like Libratran, we can evaluate the impact of these aerosol events in the surface and in the top of the atmosphere using the characterizing the aerosol radiative effect. So that's what we have in this poster.
Great, thank you. And now we are at the end of the second session. I'm sorry that we are behind the schedule. So Pavla, what did you
So
suggest?
thank you again, all the
Yes,
speakers. on
thank
the
you.
session.
Yes, exactly.
And yeah, slightly delayed, so we only have a 12 minutes break now, and we will continue again at 2 o'clock Icelandic time. That means already in 12 minutes. I'm sorry for that. But for the posters, we will have the other break after the next session.
So
Thank you.
coffee now, is it so?
Yes,
Coffee now.
yes.
Yes. Yeah.
Just stop the recording.